Thank you everyone for joining us this afternoon for this webinar entitled Critical Minerals from Lignite, the Process and Products. This is being done through sponsorship from following entities that you see online there, primarily funded through the U.S. Department of Energy, through the National Energy Technology Laboratory, and the North Dakota Industrial Commission. Along with those contributions, we also have support through Basin Electric Power Cooperative, BNI Energy, Minn Kota Power Cooperative, North American Coal. And we also have advisory input through Current Chemicals located in the state of Ohio. So thank you to all of you for sponsoring the past webinars and the webinar today. So this is a webinar that continues a series that we've had over the past little time here. And so the first three, critical minerals, what, how, and why all the hype, today's critical mineral technologies and how to move forward, and why do critical mineral business in the Williston Basin, our strengths, our assets, our needs. They have all been recorded, just like this webinar today being recorded, and are accessible through our website. And we have a link to that website that you'll see at the end of the webinar today. And so even if there are parts that you'd like to go back and review from today's webinar, you'll be able to do that. So when Charlene gets the recording posted to our site for access, we will be sending out another email to all of you that registered for today's webinar, letting you know that it is available. And so I encourage you, if you have the ability and you haven't seen some of the past webinars, please go online and get these, and hopefully they'll answer maybe some questions you might have about what this deal is with critical minerals and rare earth elements in the Williston Basin. So with that, we're just going to jump right into this. And I'd like to present Nolan Theaker, who works at the Institute for Energy Studies at the University of North Dakota. He is also involved in the core CEM program, of which I am the principal investigator, that is generating these webinars. And at the end, when Nolan is done, I'll speak for a few minutes about the core CEM program in general. But with that, though, I'm just going to jump right in and turn this over to Nolan. So take her away.
Thanks, John. So to kind of get us started, what's a critical mineral? So in general, what defines a critical mineral? It's a mineral that's either the U.S. is more than 50% import reliant on, or the supply chain feeds through a very narrow subset of companies or entities that make this. For instance, the rare earths, and we'll cover this a little bit later as well. Rare earths, the U.S. is pretty much 80 to 90% import reliant on. That alone would make it a critical mineral. But also about 95% of all of the processing somewhere in the middle of that rare earth supply chain is done solely in China. And so that narrowing of how many people interact with the supply chain also makes it a critical mineral. And really what it is, it's an umbrella term. It's, once again, any mineral that is defined by criticality in that form. And typically there's kind of one group you can pull off very easily, the rare earth elements that hopefully everyone's heard about. And really what these are, they're not rare, so to speak. They're found together, but they're rare to find in a big concentrated seam. You're not going to find like a big rare earth seam like you might see an iron seam in the Iron Range in Minnesota, or copper seams in some of the other mines. Typically they're far more dispersed. Also, the rare earths are extremely chemically similar to each other, which is why they're grouped the way they are. And once again, why they all 17 of them appear together rather than separately in individual seams. And it makes them quite difficult to separate. And I'll get into just how difficult later in this presentation. And another thing is each of these have a different use. I mean, they may be chemically similar, but they still have different properties. Some can be used for magnets, some can be used for glasses. Some of them, there haven't been enough produced for us to really figure out what best to do with it. So I'll kind of walk through some of that later. And then the other group is all the rest functionally. I mean, we can subdivide the other critical minerals into 20 different categories if we want, but realistically, there's no great common factor that makes 17 of them lump into the same basket like the rare earths do. And there are a lot of critical minerals. I'll show you kind of how many here in a minute. Now, why do we care about these? Critical minerals play an absolutely vital role in our everyday economy and our national security, from lasers and LEDs to sports equipment to alloys for aerospace and car and medical device applications, to x-rays, computing. there's basically almost anything you would do during your day is enabled by or directly involves critical minerals. And I think that's fairly safe to say. Once again, US is more than 80% import reliant on critical minerals. And just looking at the rare earths, once again, my example I used earlier, pretty much 80% of those get funneled straight through China with very limited supply from other countries. And so in essence, this kind of outlines this criticality and why domestic production of these is so critical at this point. So here's your average periodic table with your critical minerals and rare earths pointed out. As you can see, there are a lot of critical minerals. Anything in these gray boxes is a critical mineral. And for that reason, it's hard to kind of group them together apart from just they are. Now, the rare earths are generally in these blue tones. And I'll call out that you've got heavy rare earths, kind of these dark blues, as well as scandium and yttrium. And then you've got light rare earths over here on the left. What we have surrounded in yellow boxes are what we think are the elements that the Williston Basin can most likely put to market and contribute the greatest on. And as you notice, it's not all the rare earths. Once again, they're not made equally. I'd point out that these two, PRND, and these two, TB and DY, are what we call magnet rare earths. And I'll revisit that later, but that's a crux of, in essence, why separating the rare earths is such a pain, as you're attempting to get to these magnet rare earths. They're the real value. Now, what we're going to be talking about today, once again, it's rare earths from lignite. And so we're going to be focusing on just this one source. But the project and the initiative overall is looking at all of the different unconventional sources we can get critical minerals and rare earths. That includes lignite and existing or potentially even new mines. That includes coal ash, produced water, some of the shales that we found in North Dakota, as well as coal seams maybe we can't dig up and maybe we have to get to via another mechanism. But for the purpose of this call, we're going to be focusing just on the sole source, the lignite mines here. Now, this initiative doesn't just find where are the rare earths and how do we get them out of their source material, which is kind of the mining bit. We also need to get to who's going to use these, what are the final products they're going to make, and kind of iron out what a potential basinal business model from those sources to the manufactured finished goods through all of these steps are going to be. And you're going to see these steps come up more than once in our presentation upcoming. The goals of this webinar today are really to sort of answer the question, what does it take to make rare earths and critical mineral products from lignite? What methods are we going to use? How many steps or potentially involved parties and other businesses might be involved? And where do these handoffs exist to send, in essence, sell a product somewhere in the chain to someone else somewhere else in the chain? Where we're talking about processes and steps and how many different products we're going to make, we're going to get into flowcharts. So just expect boxes, expect arrows, expect a lot of them. But we're hopefully I do a pretty good job of explaining them to you so you kind of know what's going on. So we're going to start with a quick preview and kind of what the overall picture is in a general sense. So typically we're going to start at lignite, typically at the margins of the seams. That's where we find the most rare earths, critical minerals. We presented on this a bit in webinar 1. And then we'd start with this mixed concentrate plant. And what this mixed concentrate plant does in general is it pulls the rare earths out of the coal, and then it'll make a few different products. First, we have the coal itself. We pulled the rare earths out of the coal. It's still coal, and actually it has unique properties that can make it more valuable than potentially the coal that we got at the beginning. And what we're looking at here is you can make power with it as a blend fuel. You could potentially make graphite and battery components with it, or you can use it for a number of other different applications. There's probably thousands of different products you can make from coal. And in essence, this is still functionally coal coming out of the process. So we can make a lot of different things with it. Next product are the critical mineral concentrates. Now, this is specifically the non-rare earth ones. And I kind of discuss what elements we're primarily focused on there and how we're going to get those to products, but we'll make some concentrates. We'll do some refining on those. And then one of the major product spheres that these end up coming from is in the semiconductor products. germanium and gallium being two of the major elements we look at. And here we're looking at wafers for solar cells or for LEDs, transistors, stuff like that. Then the third product are the rare earths themselves. So we're going to take this mixed concentrate, we're going to refine it, we're going to do some processing, and ultimately we're going to make magnets and a lot of other different products with it. And the magnets have a whole host of other products they go into once you actually make the magnets, but you can also buy these at your local hardware store. So this is kind of the overall picture. And what I'd like to point out at the beginning is we take this lignite in, this mixed concentrate plant will make 3 products: rare earths, critical minerals, and then the coal. And then from there, lots of other products get made. So this mixed concentrate box, we're going to expand it a bit. I'm going to show you what steps are actually involved in that. It's not just you pull it out of the ground, wave a wand, and these products appear out of thin air. So what we first do is some physical processing. These marginal lignites at the edge of a seam can be kind of tough to mine. It's likely we're going to get some rock, some clays, stuff that isn't the coal itself. And the rare earths we're finding are bound in the coal itself, not in those rocks or clays. So we're going to get those out with some physical processing, put those back underground. They're still just rocks and clays, maybe a little bit wetter than they were before. And then we're going to take this coal and do some chemical processing. Here we contact it with a really dilute acid and basically just wash the rare earths off the surface of the coal, much like you'd wash something off the surface of a sponge, where this coal is very sponge-like. And then from there, we filter our coal, wash any acid off, and then the coal itself can be used for many different purposes afterwards. For the liquid, here this critical mineral rare earth containing liquid. Here, we don't perfectly get only rare earths, critical minerals. We'll get some impurities, so we try and get rid of those. Typically, it's something iron related that we drop out as a waste. And then we'll separate off the 2 products, the rare earth product and then the critical mineral product. The rare earth product is called a mixed rare earth oxide concentrate, MREO concentrate. And I'll kind of show you what that looks like and what we do with it from there. And then the critical minerals will make a few different critical mineral concentrates as well. And then once we've done that, pretty much we've pulled everything valuable out of the liquid. We either look at recycling that water back into the plant, or we potentially dispose of it through environmental means. And so that is still kind of yet to be seen, and kind of depends exactly on what this process looks like. So what does this process look like realistically? So we mix our coal in our solution here, and it looks pretty much how, if you were to mix coal and water together, what it would look like. It's pretty dark, can't see through it. Then once we filter it out, and we've got these impurities still in the solution, it's kind of reddish. That's because of the iron. So then in essence, we've got to filter those out and drop those out, and then get rid of those materials, either sell them or dispose of them. And then we get these clearer solutions where we can drop out our rare earths. That's that tan concentrate here, that's 60 to 90% mixed rare earth oxides right here, or our critical mineral concentrates from this solution. Now, you might see this tan powder and think, that isn't a magnet, and that doesn't look like it's going to be a magnet anytime soon. And you're right, there's a lot of steps that take this powder into the final products of a magnet. So let's go through that now. So we've got this concentrate, once again, this powder. We've got to refine it into a bunch of different groups, and then we ultimately will process these groups and then make products out of it. Now, the groups that we're talking about are the magnet rare earths I mentioned before, heavy rare earths, SEG, which I'll point out in a second, light rare earths, and then scandium and yttrium. Now, just before I lose you, we'll go back to the periodic table real quick. Now, I mentioned these magnet rare earths are this PRND TBDY. The magnets, in terms of rare earth value, the magnets are what dominate the industry by a long shot. Making rare earth magnets are why rare earths are a critical mineral today. It's not really any of the other rare earths that make a significant difference on that criticality, although gadolinium is pretty useful too. Then we mentioned a heavy rare earth concentrate. That would in essence be everything over here to the right of these magnet rare earths. We've got this SEG concentrate, the SEG, samarium, europium, gadolinium. That'll be in essence these 3 elements kind of in the middle between light and heavy rare earths, halfway in between. And then you got the light rare earths. that are lighter than, once again, these magnet ones. And that's lanthanum and cerium. We kind of talk about them. And here you have scandium and yttrium that are still rare earths, but aren't on this series. So looking back at this flow sheet, these magnet rare earths, you'd want to turn those into metals and then alloy them with the right metals and in the right ratios to make a magnet. Produce your magnet, maybe coat it with something like nickel or something like that to make it look prettier and be a little bit more durable. And then put this in a trillion different products. You can sell these at your local Menards or Lowe's. You can put these in wind power or in wind turbine motors, disk drives, million different applications. Your heavy rare earth concentrate, I mentioned that HO to the right. It has a few products, but ultimately the markets typically aren't large enough to really know how valuable these products really need to be. And so that's why this box is yellow and not green, is because it's one where we're not entirely certain that you could sell this all the time. And so it's kind of undetermined whether we can make it an element you'd really focus on or not. So that's why the box is yellow. This seg concentrate, europium's used for phosphors for light bulbs and TVs. Gadolinium's a key component in X-rays. And so this is obviously filled with products you'd want to separate. Your light rare earth concentrate, lanthanum and cerium I mentioned, ultimately they have markets, and they have big markets in catalysts and glasses and stuff like that. But ultimately these two elements are overproduced to make enough magnet rare earths for the whole industry, that these really are overproduced in their market. And so whether or not you can actually sell these for a profit or whether you would just dispose of them are kind of unclear, which is once again why we have this yellow box instead of green ones where we know these are going to be valuable. And then our last group, scandium and yttrium, you'd want to separate that into a scandium metal that would make scandium aluminum alloys, which are as strong as steel but as light as aluminum. Obviously really valuable for the aerospace industry, as well as sports equipment, which is currently one of the big uses for it right now. You like strong, light golf clubs. And then yttrium, which is used in ceramics, not exactly the ceramics you're going to find that make up your dinnerware, but more of the ceramics that are going to be in furnaces for thermal management and some mechanical properties. So this refining box, I pointed out and I just say, oh, it happens. What does it entail? So there's three kind of paths that you can refine the rare earths. There's a chemical path, an electrical path, and a physical path. But really, industrially on large scales, chemical refining is the dominant path to date. Typically, it's solvent extraction. And what this involves is a piece of equipment like this over here on the left. You'll mix in your water with your rare earths in it and an organic fluid like kerosene or something like that, something that won't dissolve in water, and an organic extractant that's kind of selective for one of the rare earths in particular. So I'll stir it up and I'll let these two phases separate, where I'll have an organic fluid on the top maybe, and then a water on the bottom. The water has the rare earths, but a little bit less of the one that was selective for that organic fluid. The organic fluid has still some of the rare earths, but more of that one rare earth we wanted. And in essence, we just let the organic fluid drop off, and there we've got our separation. We've got one stream here and one stream here. Now, that sounds pretty nice, but what isn't shown here is the rare earths, once again, are very chemically similar. So any method for separating these is going to be extremely difficult. In looking at some flow charts for industrial processing and in mining right now, just to separate out yttrium, one of the 17 elements, took 98 steps. So this is take 98 times 17. There's thousands of steps potentially to separate all the rare earths into each of their individual components. This is a very, very challenging process. So, I mean, technological breakthroughs is not, we can do this in one step. It's not even we can do it in 5. It's typically maybe we do it in 10 or 20. That's still 5 times less than anywhere else. But I mean, that's still a tremendous amount of equipment and processing to do this. These are not easy separations by any means. So once again, looking at the products of this and kind of what this looks like, we've got this concentrate again. We do hundreds to thousands of steps to separate these into these individual powders, these oxide powders. Think of this more as rust rather than metal. Now, these powders, interesting for the rare earths, just as a note, individual rare earths actually kind of all have different colors. This is one of the first uses when they started separating them is neodymium here, which is one of our magnet rare earths, makes this pretty purple powder. And you're like, oh, that's kind of useful, but that's still not a magnet. So we've got to turn that into a metal. And typically I want this about 99.9% pure. When I turn this into a metal, and this picture actually shows it very well, this metal is not air stable. Kind of like how when you have an iron fence or something, you just leave it out and air and water hit it and it's just slowly rusts and it's no longer metal anymore. The rare earths do that, but a whole lot faster, and you don't need water. It's just air. If you let air touch this at all, you start getting these kind of rusty pockets appearing on it. So to actually keep this as a product, you have to keep air away from it. So you have to put this in nitrogen or argon environments to transport this. It's just a pretty large pain, to be brutally honest. And then finally, after all this pain and processing, we get to this 27% pure rare earth magnet. And this is a neodymium disc magnet. It's actually pulled off Amazon. You can buy this very magnet. And you're like, why did we go through these thousands of steps to make this little magnet that's not even that many rare earths in it? Well, here's why. This little magnet is 10 times stronger than your black ferrite fridge magnets that you might have. It's lighter and it's smaller. And so you might, so if you can start to think about, well, where would I want a light, small magnet that's strong? A lot of places. So if you want a small magnet, your magnet in your cell phone would be really useful if it was small because it's already a lot of stuff in the cell phone. You want a light magnet, something you take up into the air, like a plane or a missile. You'd want obviously to be light, that you don't have to move that much weight around. So this is why the magnets have pretty much dominated the industry for rare earths. Anywhere you want a magnet that's strong, light, and small, you need these. Now, let's step through the second of those products, the critical mineral ones. And once again, I'm going to just disclaimer, this isn't all the critical minerals that can be produced. Pretty much everything on that periodic table exists in coal. Here, we're just kind of focusing on three of the most likely valuable ones from lignite in this process, and that'd be cobalt, germanium, and gallium. Here, in essence, we take our refining and in essence produce our powders and then get these into pure concentrates, from which we then turn these into metals and do whatever we need to make these different products. Now you'll notice this is ultra purification here for germanium, and gallium in essence to get the semiconductor metals needs it too. So what does that entail? Rare earths, once again, I said it's 99.9% pure. That'd be 3N. The absolute maximum you'd need to purify rare earth would be 5 nines, 99.999%. These semiconductors can take up to 6 to 12 nines of purity. And here's what 12 nines look like. That is a whole lot of nines. Or you can think of it as 100 million times more pure than the rare earths, which is mind-boggling to think about. Just to get from 11.9 purity to 12.9 purity, if I have a rail car of metal, I need to remove a solitary milligram of this stuff. This is such a tiny amount of material. I mean, think of the tiniest little pill that's 10 milligram pill. I need 1/10 of that to purify this from a rail car of material, unimaginable quantities. And how we do this is a process that's kind of produced this way, and that's the Szoralski process. Forgive my Polish. But it's a process named after scientists where basically I melt a big portion of this metallic semiconductor and I melt it really slowly. So at the very tip here, that's where impurities tend to congregate. So I can in essence cut that tip off and then remelt it again. A little bit more impurities will get here and I can cut that off and keep going. So what these products we're going to make from these semiconductor metals are going to be like transistors for computers or LEDs, lasers, and optics. And for these two elements specifically, the US is more than 90% import reliant. And this has been identified as a key weakness by Department of Defense suppliers, not suppliers that want to be identifying weaknesses typically. Additionally, once again, I mentioned that cobalt for lithium-ion batteries. I'll also mention graphite here in just a second when I get to the carbon products. But these two are the primary constituents of both electrodes in a lithium-ion battery, the positive electrode and the negative electrode. And ultimately, I mean, you hear lithium-ion battery, oh, we need lots of lithium and lots of lithium, and lithium's expensive. Well, realistically, cobalt and graphite account for somewhere in the territory of half the cost of the battery. These are not cheap materials. Obviously, lithium is needed as well and is another big portion of the cost, but these are no small potatoes either. Now, we'll finally get back to this critical mineral depleted lignite and go through this third product here. Now, there are about 1,000 different carbon-based products, probably more than 1,000. I don't claim to know all of them or want to put you through a lecture where you go through all of these. But really what we're looking here is a few products that take advantage of some of the unique properties of this critical minerals depleted lignite. One of these is just as a blend fuel. We get rid of some of the contaminants that are annoying for the boilers like sodium to burn. And so we could potentially make this into a better burning, potentially lower emission electron or lower emission power through this fuel, which would be good. We could turn this into graphite by making pitch or a couple other processes, and that would give us the graphite you need for those lithium-ion battery components. Or we could purify the organics out of here and potentially make fertilizer out of them like humic acid, or turn this into a sorbent that can pick up wastewater ions or something like that. Now for carbon products, one quick point is there are a lot of different carbon products. So you need to think about is the value of the product and the market size of the product. Now, the value of a fuel, how much you'll pay for this lignite to burn it as a fuel is a whole lot different than what you pay to make this graphite. However, I can use billions of tons of coal to burn for power. The graphite market would absolutely implode if I put even 500 million tons of graphite suddenly on the market. And so you need to think about when we're looking at these carbon products, what's the most valuable products that I can make where I don't completely shatter the market by introducing this into the market? And that's where obviously some of those business considerations need to come in. So it's kind of like a summary diagram, the quick summary diagram. We've got this coal, we extract out our critical minerals and make rare earth critical mineral products. We've got this critical mineral depleted lignite that can either make electricity or go into these or produce these carbon-rich materials for graphite, graphene, or a number of other products. So kind of in summary, there's a lot of steps in this process and a lot of potential handoff points to get from the mined lignites to the products. These different products require vastly different purities and vastly different processing methods as you move through this. To point this out, I mean, this isn't going to be one giga plant that's located right by a mine. There's probably going to be a lot of different facilities producing these products and doing some of these separations, and potentially in a lot of different locations. This doesn't have to just be in one spot. Then, as just a quick note, shipping solids is pretty easy over a long distance. I can just pile something up on a truck and then just drive it somewhere. I can't exactly pile up this organic solution I talked about earlier on a truck and ship that. So in essence, where another company has to come in is kind of typically set on what's easiest to ship or move from place to place. If it's hard to move, typically you don't want another company doing it. And then once again, because of this, anytime a solid is produced, because those are really easy to ship, that can be another business. So now kind of walk through step by step and kind of join all these diagrams we saw. So we've got the lignite and the margins. That's obviously a lignite mine that exists today that could potentially mine this lignite. This mixed concentrate plant could produce up to 4 separate products, which are what these green boxes are. The critical mineral depleted lignite, the concentrate, and potential critical mineral products. And then when we go into the refining, there are a million different products you could make. You could stop your refining process at making those separated purple powder that you can then sell to someone else to make metal, who sells it to someone else to make magnets, who sells it to someone else to make disk drives. And so in essence, you could stop at those powders. You could purify them more to the products that they need. You can metallize them. Many, many, many different applications here. In the critical mineral space, each separate ultra purification step and metalloizing and alloying step that you have for each of these concentrates can be a separate entity who could then sell that to yet another entity who actually uses these semiconductors or makes the lithium ion batteries. And then finally, on the carbon products, each of these, pretty much every company could buy this lignite and do a million different things with it to make a million different products. So this is many, many, many different companies that could exist from here. This isn't just one massive company, and this isn't just a few hundred jobs we're talking about. I mean, this could be realistically 100 companies employing each 100 plus people. Now, while this is huge and overwhelming, and you think, oh, how are we going to be able to do all this? I want to point out at least that the most recent grant award that UND's got for doing a front-end engineering design study and engineering study on this actually covers all the way from the lignite at the margins to metallizing these rare earths. And actually, if we're successful in that grant, the construction of a plant like this could begin in 2025, just 2 years from now. So this isn't a very far off dream that we're thinking of having this. This is actually a lot nearer term than what might have been thought possible. So with that, I'll go ahead and conclude and thank you all for your time, and I'll turn it back over to John.
Yeah, thank you, Nolan, for that. I know everyone, it seems like it can be very complex, or at least maybe not as straightforward. And hopefully that has answered more questions perhaps than it has created. And on the note of questions, I've got just a couple more slides I'd like to step through. And then if you have questions, please feel free to use the Q&A or in the chat, either way, and we'll get to questions here as soon as I wrap up. This webinar, along with the others, is funded through a program that we call the Williston Basin CEM Initiative, which is part of an overall Department of Energy program. And CEM stands for Carbon Ore, Rare Earth, and Critical Minerals. And so in this instance, we're not looking at coal as a fuel source. We're regarding coal as an ore that can be mined. And so it may be a bit of a mind or a thought shift or a concept shift for many. But the purpose of the CEM program, again, looking at those communities who historically have relied very heavily on the mining of coal and the use of coal, primarily as a fuel and a few other products. And as our concepts and thought processes around power generation are changing and what we're looking to do in the future, they want to make sure that those local economies are not left behind, that there are ways to still create new jobs in those regions, catalyze economic growth, and at the end of the day, kind of strengthen our national economy and security, especially in light of things that affect world market. And of course, the most recent thing has been the conflict with Russia and the Ukraine. That greatly affected world markets, which did absolutely affect price on critical minerals and rare earth elements. And so this is a program then to start looking at how to utilize what there might be in the United States. I describe it as the main goal of this program is to identify what's there, characterize what we have, and then assess how that may be utilized in the future and start to develop plans on how to move through that. So there are 13 core initiative teams across the United States. We are the Williston Basin, so we're number 6 in the gold. And for those of you that are savvy with coal and where it's found in the US, yes, you'll see that these are directly related to where those coal deposits are in the United States. But we're number 6, the Williston Basin, which covers North Dakota, a small bit of South Dakota, and a little bit of Montana. So you'll see here with this core project team, it's a well-diverse team made up of folks not only in North Dakota, but Geologic Survey of South Dakota and the survey in Montana through Montana Tech. But it's also made up of utilities and mine companies. It utilizes expertise from the University of North Dakota State University, very diverse. Thank you to all of those project team members for your input on the project. Just real quickly, we'll do the typical disclaimers. Information that was presented today is not done through the voice of the Department of Energy or the North Dakota Industrial Commission. Thoughts and conclusions are strictly due to us, the presenters, no one else And likewise, if we happen to mention a particular technique or product, the North Dakota Industrial Commission and the Department of Energy are not promoting those products and are no way associated with that. For the future, stay tuned. We are planning additional webinars in our series. We're looking at doing something in the August timeframe and in November, and we'll have information coming on that soon. And also to put in a little teaser, some of you may have attended last year's Critical and Rare Earth Element Symposium that we held in Bismarck, North Dakota last October. We are planning a second symposium. Details will be coming soon on that, but we do plan that that will take place on October 9th and 10th. Please stay tuned as we finalize the details on that. We'll be sending that out to all of you. And with that, we'll stop and we'll open this up to questions. So Charlene, do we have any questions on the board so far?
So at this moment, we have a question and a comment. And I would also like to say, in addition to putting your questions in writing, you are certainly welcome to use the tool at the bottom of your screens that invites you to raise your hand under reactions, and then you can unmute and ask a question. So comment, great overview, sir. This is to Nolan, explained in a way that is digestible to everyone. So mission accomplished, Nolan. And the question is, at the risk of asking questions that were probably answered in previous webinars, what is your overall sense of the sustainability of these businesses that would be created? It makes obvious sense, to me at least, the writer, that we should be as self-reliant as we possibly can, but I don't see that happening in Washington. Do you think that the optics of coal, not the reality, might make policies that would make it hard to function as a business?
There's a lot buried in that question.
Yes.
So I'll kind of step through it. I've got the question up on my other monitor. So first part, what's the overall sense of the sustainability of these businesses? The rare earth market is a challenging one, the critical mineral one as well, not least of which because it is highly politically influenced around the world. If one company decides to suddenly subsidize their industry, drop the price, companies might be in a real hurt suddenly if those subsidies are strong enough to in essence start pushing market entrants out. In terms of a sustainability aspect, I think the US is starting to go down a path where they realize that in essence, if you just let free rein and just say, well, the market will take care of it, any country such as China, for instance, in recent history, can drop prices, subsidize their industry, and then cause that market to fail. But what the US is doing now, which I think is good, this was in the Inflation Reduction Act actually, was this EV, the electric vehicle tax incentive they had, is based on what percentage of your critical minerals in that electric vehicle were made from the United States. And so if you make your EV with essentially zero critical minerals in the US, you aren't allowed to claim that tax write-off. And so basically it creates almost a separate market for US-based critical minerals because there's going to be potential tax implications for that industry. And I think it's things like that which will start to help develop a new industry and bring this back to the United States and then actually get it off the ground and keep it stable. In terms of sort of the optics of coal and what this will be based on, really the question to me becomes, do we want critical minerals in the United States? And if we do, mining has to be done. Absolutely no other way. The point about doing coal is I don't have to build yet new mines that might take long times to actually permit or could potentially run into environmental problems that aren't aware. These coal mines are already up and running. It's basically just taking advantage of existing assets rather than in essence trying to take risks on potentially new assets that might take a while. So it's one that, while obviously coal in some spheres can be seen as a highly negative thing, in this case, I would define it more as, look, you're mining for these critical minerals, and if the coal happens to be a part of the process where that's involved, that's great. But in essence, if it's not involved, then this is 10 years or 20 years away instead of 2 years away as it currently sits. So that's really kind of where I'd push back on that optics of coal problem.
Thanks, Nolan. Do we have any other questions or comments or responses to what Nolan had to say?
Just mention real quick here to Charlene, you put in the chat the link to our website. The link is there that you can access the other webinars that have already been conducted.
Mm-hmm. Yes, I did. And we have another question. This one says, considering there are a lot of steps to take the lignite to these end products, how would that compare to recycling on rare earth elements, such as neodymium, in existing products? So obviously these aren't mutually exclusive, but is recycling much harder than this lignite processing despite the number of steps?
So one thing I'd mention about recycling is, in terms of recycling, if we're talking about magnet recycling specifically, it has yet other steps that aren't based in this process because it has to basically break down magnets. Magnets like staying together. Basic form of magnets. So there's additional steps that go into recycling something like a magnet that this process won't have, which add challenges. Whether or not those are better or worse, still yet to be seen. In terms of separating the rare earths, like if I have this neodymium magnet and I say, you know what, I'm going to get the elements back out and then remake a new magnet, I still have to separate all those elements out. So I still have to, in a lot of cases, go into those really painful, laborious separation processes anyway. And at least in the refining and the processing methods, I maybe don't have to touch lignite, but I still have to go through a lot of those processes anyway. And something I also would point out is, at least in terms of a stability of a market base, one advantage, at least I think, of the proposed flow sheet that I showed is that there are the three main areas of products. It's not only rare earths. Once again, I mentioned the rare earth market can be very volatile based on international politics. If you're building a business based on a market that can increase its price by 5 times or drop its price in half on, in essence, any given year, depending on what countries are doing around the world, it makes it challenging to really produce a business from it. Whereas if you have these other products that can kind of stabilize your income, a business might be more sustainable that way. See another question. Seems like the DoD will need to provide a stable customer so the Chinese cannot put nascent suppliers out of business. Is that formally happening? I've seen a few points where it looks like the DoD and DOE are starting to think about actually providing a floor price where basically they'll buy anything under a certain price for the rare earths, just to, in essence, somewhat stabilize things. But I haven't seen any formal completion of that yet. I know there's talks. I know industry really wants it to happen and thinks it's necessary. I would generally say I would agree. It looks very good, but at the same time, whether or not that's going to happen is sort of a political question, and that's not something I think I have the ability to answer. That would be more DoD, DOE answering that question on whether they think they could do it or not.
So we also have a response. Nolan agreed. Andrew's agreeing with you. The easy ability to add other revenue streams is exactly what makes this so enticing. Rona asked, are the rare earth element specific organic fluids you mentioned information that you can share, or is that information proprietary?
It depends. There's a lot of publicly available known solutions that you can use. DEPA, DHEPA is one of them. It's a complex organic molecule that can capture the rare earths and slowly split them. There's a lot of different molecules in the literature that can do this, but there's also proprietary ones that maybe can do it in a few less steps than other processes. I mean, additionally, there is active work in those electrical pathways to try and electrically separate the rare earths, not chemically, but typically they're still finding it's still multiple steps. It just may not be as many steps, but it's still multiple steps is the problem pretty much with any process.
Okay, thank you. And so we do have a team of university interns who are listening in today. They asked about the magnet processing, and it was indeed magnet or RE recycling, and it was indeed magnet recycling they were specifically talking about. And so just to confirm, the processing methods differ, but would be likely comparable in terms of difficulty.
There are extra processing pieces that you'll have to do, but when you get to, okay, and now I have iron and boron and these other rare earths and maybe a couple other elements added in, and I have to separate everything into their constituent elements, I basically run right back into the refining box that I mentioned was one of the hardest boxes of separation by far, where you have those hundreds of steps involved. Now, obviously, you don't have all the rare earths. You only have the magnet ones. So there's some advantages there. But then there's also the disadvantages of typically you aren't just getting a magnet. You aren't getting a truckload of magnets delivered to you. You're getting a truckload of old computer parts that then I have to shred those and get to the magnets. And then I have to burn the magnets to demagnetize them at a high temperature. And then I have to strip off the coating. And then I have to separate this out and then do all that processing again. So it's not that it's necessarily the same processes, or in essence, some of the same processes that are used, but there's a lot of extra processing that's required. But there's some advantages where you don't have lanthanum and cerium around, so that makes things easier as well.
And so the cost may be,
Could be higher, could be lower. I don't see being able to recycle 100% of the magnets as a realistic option for, I can recycle magnets, so I don't need the magnet rare earths ever again. I don't think that's plausible. But what I do think is it can probably fill some of that gap if, in essence, all that processing ends up being cheaper. I know there's some companies that are looking at standing up processes for recycling and focusing on magnets and focusing on a few other things, but it really depends on what elements you're going after, what source material you're getting, and how much processing does it take to get into a separable form to really see if your economics are going to work or not.
Okay, thank you. And I just want to clarify for the sake of the program, this is coming to you as part of the core CEM program. And so everything Nolan says about recycling is not what the core CEM program is working on. That is not part of the venue with respect to core CEM.
Yeah, if you're absolutely horribly mad at somebody for saying all these things, it's me. It's not core CEM or the ERC, just me.
Nolan is speaking to his expertise, not from the core CEM program. Just a little disclaimer there. Tangential question. Andrew was being told about some work being done on using coal for battery anodes. Do you know anything about that specifically?
I know there's 2 or 3 different projects looking at trying to make battery anodes from coal. 2 very specifically on lignite, one done at the University of North Dakota. I think the other one was George Washington University. I believe so. And really it's trying to use that organic matrix that houses the rare earths. It ultimately ends up being a very pure organic form that if you turn it into graphite becomes very pure graphite. That would be great for batteries. And so kind of where this process fits in is if we get all that stuff out of that organic structure, all these rare earths, critical minerals out of the organic structure, it just makes it that much purer, which should presumably make a better battery grade graphite. In terms of knowing specifically about that, I can refer you to people. I'm not the battery expert, either at IES or in general. My world is rare earths and digging things out of the ground.
Okay, thanks. And Andrew says, by the way, I wasn't being lazy. I was just curious about your thoughts on them. Thank you. Andrew, we didn't think you were being lazy.
No, not at all. It's just unfortunately, I don't have a whole lot to add. I just know there are projects ongoing and a couple of them are lignite based.
We in the science world have learned that the more you know, the less you know.
Yes.
I don't know, Nolan and John, if we are going to have any more questions this afternoon. So
All right,
If not,
well, yeah, I guess I'll thank everybody. Nolan, thank you very much for presenting this afternoon. Thank you everyone for attending the webinar today.